Have you ever stared at an equation and just felt completely lost? Well, today we're going to crack that code. We're going to learn how to sketch graphs and turn these abstract formulas into pictures that tell a really clear, intuitive story.
So here's our game plan for today. We're going to start with the absolute basics, the parent function. Then we'll build up our skills, first with some simple transformations before we bring in the heavy hitters from calculus to find all the juicy details. By the end of this, you'll be able to sketch even pretty complex functions with a ton of confidence.
You know, every graph kind of has a family, and at the head of that family is what we call the parent function. It's the simplest, most stripped-down version of a shape, and it's where our story always begins. Okay, check this out. On the left, we've got this simple, clean V shape. That's the absolute value of x. But then look at the right. It's been flipped upside down. It's been shifted over. I mean, they're clearly related, but how in the world do we get from one to the other? That's the puzzle we're about to solve.
Yeah, this is the big question, isn't it? How does this super simple shape transform into something that looks so much more complex? Stick with me and you'll have all the tools you need to answer that question yourself.
First up, let's open up our pre-calculus toolkit. These are the fundamental moves, the basic transformations that let us take our parent function and really start to play with it on the graph.
So this is where it gets really cool. Notice how if you add a number times outside the function, the whole graph just moves up or down. But if you do it inside the function, right there with the x, it moves it left or right. It's kind of like we're just giving our shape a brand new address on the coordinate plane.
Let's see this thing in action. We start with our basic parabola, right? That y equals x squared. Now, that -2 on the inside with the x, that scoots it 2 units over to the right. And the +1 on the outside, that lifts the whole thing 1 unit up. And just like that, we've moved our shape to a completely new spot.
All right, next the graph over the x-axis. But put that negative sign inside, just with the x, and it flips over the y-axis instead. It's all about where you put that negative. And finally, we can also stretch and shrink our graph just by multiplying. You can think of it like pulling on a rubber band. We can make it taller, shorter, wider, narrower. So with these three tools, shifting, reflecting, and stretching, we have complete control over that parent function. But what about the really interesting parts of the graph? You know, the peaks, the valleys, the exact spots where the graph changes direction. For that, we need to level up our toolkit. It is time to bring in calculus. This brings us to a really important idea, the critical point. You can think of these as the VIPs of our graph. They are the only places where we can possibly have a peak or a valley, a maximum or a minimum. And we find them by figuring out where the first derivative is 0, or maybe where it just doesn't exist.
I absolutely love this analogy. The first derivative is basically our function's compass. If the derivative is positive, we know we're heading uphill. If it's negative, we're going downhill. And if it's 0, well, we're on flat ground, which means we're at a potential peak or valley.
And this gives us a super powerful 3-step method for finding the absolute highest and lowest points on a graph. The key is, you just check the function's value at all those critical points we just talked about. And you also check it at the very edges of the interval you care about. Then you just compare them. The biggest value you get is your max, and the smallest is your min. It's really that simple.
So we know if our graph is going up or down. But how is it curving? Is it bending upwards, or is it bending downwards as it moves? To answer that question, we have to go one level deeper and use the second derivative.
The second derivative tells us all about something called concavity. If it's positive, the graph is what we call concave up, kind of like a cup holding water. If it's negative, it's concave down, like a cup that's spilling water. This little detail is all about the specific bend in the curve. And what about the exact moment when that bend changes direction? Well, that's called an inflection point. It's the spot where the graph switches from being concave up to concave down, or the other way around. And we find these by looking for where that second derivative is 0 or undefined.
All right, we have our full toolkit. We can move, flip, and stretch. We can find all the peaks and valleys with the first derivative, and we can understand the curve with the second. So now it's time to put it all together and tell the complete story of a function totally from scratch.
And here's our subject, a cubic polynomial. I mean, you can't just look at that and know its shape, right? We have to use our calculus tools to really uncover its secrets.
First, we use the first derivative. This tells us where our function is headed. We can see right here that it's climbing up until x equals -3, then it drops until x equals 1, and then it starts climbing again for good.
We just found our local peak and our local valley.
Next up, the second derivative tells us about the bend. And look, it's spilling water, concave down, all the way to x equals -1. And then, right at that point, it switches to holding water, concave up. We just pinpointed our inflection point.
And here it is, the complete story. We can actually see the peak, the valley, and that crucial inflection point all coming together to create this beautiful flowing curve. Every single piece of information we uncovered is right there in that final picture.
So that's really our toolkit, right? We start simple with a parent function, we reshape it with some basic moves, and then we use our derivatives to find all the interesting details. It's a system, a process for turning any equation into a picture.
You know, we've been working in this familiar world of x and y axes this whole time, but what if we changed the fundamental rules of the game? What would happen if our graphs weren't based on a grid of straight lines, but on circles?
This is a graph made in polar coordinates. All of a sudden, our equations can create these stunning symmetrical flowers. It's just a powerful reminder that every mathematical tool we learn doesn't just give us one answer, but it opens up whole new universes for us to go out and explore.